Hello and welcome to the Weekly Space Hangout for Wednesday, May 16th, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about what's going on with the International Space Station. The Galileo flew through the plumes on Europa, a helicopter from Mars, the Block 5 launches for the Falcon 9. How would we know if life could survive in the multiverse, and stars found at the earliest moments of the universe? Joining me this week, we've got two out this week, but we've got one in. We've got, of course, Morgan Renberg. Morgan.
Hey, Fraser. Good to be here.
And our special guest, who's going to be both, I guess, Kimberly and Paul, is Dr. Ethan Siegel. Ethan, welcome.
Hi there, everybody. Pleasure to see you, and welcome to the Weekly Space Hangout.
I can't believe we've never had you on the Weekly Space Hangout. That's super interesting.
It seems impossible.
Yeah, but here you are, and I guess it happened. So
You know, now that the stars have aligned, I have a feeling you'll be back, and so will I.
perfect. I've done a bunch of episodes of The Guide to Space with Ethan. Did one a while back. Another one is coming out in just another week or so, all about space time, which is going to be great. So let's get into the interview portion so you can kind of know who Ethan is, and then Ethan's just going to help us out with the news. All right, so Ethan, Dr. Ethan Siegel, tell us who you are, what you do.
Sure. My name's Ethan Siegel. I'm a theoretical astrophysicist. I first met Fraser just about a year after I had finished my PhD. I graduated with my degree in theoretical astrophysics, specializing in cosmology from the University of Florida. I worked at University of Wisconsin for a year. I did a postdoc at University of Arizona, and it was at an American Astronomical
Yeah, I
Society
remember.
meeting
We
that
argued
I
about
first
dark
met
matter. Well,
Fraser.
you
I had a
explained.
ton of hair up
Yeah.
here, none over here, but time does what it does, and
Yeah.
you have to adapt. And after that, I moved to Portland. I was a professor of physics and astronomy at University of Portland, and then Lewis and Clark College from 2008 till 2015 was the last time I taught. And since then, I've also been writing the blog Starts With a Bang, which I started in 2008. And that is what I do full time now. I'm a science communicator and the author of 2 books, Beyond the Galaxy and Treknology. And I'm currently writing a 3rd book called Before the Big Bang.
Oh, really?
There's my 2nd book, Treknology. I've got a copy
Yeah,
too.
we got 2 copies side by side. Hold it up again. There we go.
Got to get Morgan in on the action. You're
Yeah, he
missing out,
doesn't
buddy.
have one. So,
That's right. Just give us one of these. You'll fit right in.
yeah.
But that's what I do, and I'm super happy to share whatever stories about the universe I can with anyone and everyone willing to listen, which doesn't make me too different from people you're used to seeing here on the Weekly Space Hangout.
So let's talk a bit about Starts With a Bang first, and that is, I'm going to give you giant kudos. I read everything that you write. I would say, I'm a huge fan of the work that you do, because you are one of those science communicators who has the deep knowledge. You have your PhD in cosmology. You or you're an astrophysicist specifically, right?
Yeah.
So you have the
So
scientific
technically, my
background.
PhD is in physics. I got it through the physics department. So you have to learn all the things: quantum field theory, general relativity, particle physics, high energy physics, all of the good stuff. And then you also have to know all of astronomy and all of how stars work and all of nuclear physics. And that's part of why I love cosmology so much, is because if you want to understand the whole universe, then you need to understand what the universe was like at the moments of the Big Bang. After hundreds of thousands of years when you're forming neutral atoms, after hundreds of millions of years when you're forming stars and galaxies, and the physics of dark matter and dark energy and how it all evolves and how it will evolve into the far future. So I think about cosmology in terms of, on the one hand, there are only a few thousand people in the world who study it and know it at the level that you do when you go and get your PhD and do a postdoc and become a professional cosmologist. But also, this is a story that all of humanity has in common, that everything on Earth has in common. We all share this same cosmic story, and the idea that you would have to go to school for 10 years to specialize and learn and study this to understand it, that has to go for me. When you see a TV show like Cosmos, I think that's great, but wouldn't it be great if you had someone who was an actual cosmologist who knew this stuff in and out,
Mm-hmm.
presenting that information? And so that's an eventual goal that I'm working towards. When I think starts with a bang, I think, you know what? That's what this is. This is the whole story of how the universe went from a hot, dense, expanding, uniform state. And even before, if we talk about the science of what set that up, to this vast, enormous, rich universe we have today and how it'll continue to go into the far future. This is a story for everyone, and we can focus on tiny different parts of it or the whole story at once, and it's still something that should be accessible to everyone. So it starts with a bang, written at a professional level,
Yep.
but no equations and lots of illustrations.
Yeah, and I think that's a big thing with your website. Oh, go ahead, Morgan. I was going to jump in there, but go ahead.
I was just curious what you think that we as a scientific community could be doing better to break down some of those barriers and the impression that, yes, you have to do, 9 or 10 or 11 or 12 years of education before you can appreciate and talk about and understand some of these really big, important ideas that we talk about all across the sciences.
Well, the biggest one is you have to be the example. The biggest one is you have to be the example of saying, like, hey, we don't know, like, oh, I'm a layperson, I'm not an expert in this. You have to recognize that there is a set of knowledge out there that you don't know, and you have to be willing to listen. But at the same time, you need to go to the right people to say, who is giving me the accurate information versus who's doing self-promotion, who is trying to say, like, hey, listen to me, I'm awesome, and you want to hear what I have to say. Yeah, at some level, I suppose everyone thinks that, but this isn't about me or anyone else. This is the full suite of knowledge that everyone combined has synthesized to teach us the best, most accurate conclusions we can learn about the universe. That's the story that needs to be told. For every part of that story, there's what we know and why we think we know that, how we came to know that. That's the part that I like to tell. And the way I like to tell that story is I like to start at a point where I think, you know what? Everyone who's intelligent and curious, but not knowledgeable, can start here. And then if you can start here, we can take a little step to say, oh, well, if you start here, then this is how we get to that next step. And then you can take another step and so on. And by time you get done with a little piece of a story, here you are at a place where you would have been very uncomfortable if you had started up here. But because you started someplace you were comfortable and you went step by step by step by step by step, you wound up at a place where you could say, oh, and now I understand why people think dark energy is real. And now I understand why we think we live in a multiverse. And now I understand, right? These big questions, they can be understood conceptually. But a big part of that is making a big effort as a science communicator to speak to your audience at a level that doesn't talk down to them, but also respects where they are and doesn't talk over them.
I mean, one of the things, like, if you look at, I'm just putting up your blog right now, and like listen to the topics that are there, right? When will we break the record for the most distant galaxy ever discovered? How close could two alien civilizations get to one another? We still don't understand why time only flows forward. How big will the universe get? The multiverse is inevitable and we're living in it. Like, one of the things that's great about you, and I don't see a lot of other science communicators tackle it, is on the one hand, you're willing to take on the really out there topics, the ones that a 4-year-old would ask, right? Why is there something and not nothing? Where is everything going? Where did everything come from? Like those really big, that a lot of scientists actually wouldn't really want to touch because they're they can lead into philosophical territory. But at the same time, science does have a lot to say about a lot of these topics, and you're able to bring very accurate, very cutting edge science to the conversation to at least map out the terrain a bit, so a person can wrap their head around even like maybe know what are better questions to ask. And so how do you, how do you feel about that? Because I don't see a lot of other science communicators that are sort of paddling in those same waters as you are.
Well, thank you. I'm very humbled that you think so and that you think I do a good job of that. I do strive for that. But I think one of the big important things that I try very hard to do is I try and understand where the limits of science are, where they are in practice and where they are in principle. There are a lot of people who stay away from that, sort of the edges of what we know or what may even be knowable, because they're afraid of getting into a religious territory or they're afraid of getting into a philosophical territory. And I have to say, like, you can't be afraid of that. You have to understand, like, people say, like, oh, the Big Bang, that had to be the beginning. You can't talk about before that. And I'm like, well, you can't say everything about what set up the Big Bang. But just because you don't know everything doesn't mean you don't have some set of valid knowledge. So let's be honest about that. Let's take you up to the limits of what physics knows, of what physicists know. And if we want to speculate, we can talk about what the speculation is and why people speculate in that direction. But let's not mix that up. Let's not mix up what's speculative with what we're much more certain of and what's been observed and confirmed and grounded in reality. There's also a thing that I'm very passionate about where I think a lot of people don't feel comfortable concluding that things are real when you only have indirect evidence for them. And I disagree with that. I think you can be very certain that things are real when you don't have direct evidence of them. I think gravity is a tremendous example. You can't observe gravity directly. You can only observe the effects of gravity. But nobody really doubts the existence of gravity. Well, we can do the same thing when we start coming up with these theories that sound out there to people. They think about the Big Bang or dark matter or dark energy or inflation or the multiverse as being extremely speculative. And I will grant you that there are aspects of them that require you to make inferences, but they are not on the same footing as angels dancing on a head of a pin. There are things we can know and sensibly say. And then there's territory where you have to make extrapolations. When you make them, just be honest about that you're making them, and this is an extrapolation, but then continue.
Right. Use all your weasel words. So let's talk about your new book then, because that's going to lead right into Treknology, which is just a book completely filled with technology that will never be real, right?
Boo, boo. So what I did, I, like many people, I fell in love with Star Trek, The Next Generation. That was the series of my youth, of my preteen and teenage years. And it was when I was a teenager that I discovered it for real and was like, I have to see all the episodes. I have to get into this. I had always been into space. I had loved it. As someone who grew up in New York City, the night sky was a real treat to me. It was something that I only got to see on like special occasions, if like I went upstate and got to go camping. I remember one night when I was maybe 11 years old, I was up in like the Catskill Mountains, which is about 2-3 hours north of New York City. And I was laying down in this field of grass, and it was just this beautiful, clear, dark, moonless sky. You can't see the Milky Way, but there must have been like 1,000 stars in the sky, and it was a gorgeous sight. And I remember digging my hands into the blades of grass in the ground as I laid on my back and looked up, feeling for the first time like if I didn't have this planet to tether myself to, I would fall up into the abyss of space. And that was like a very compelling moment for me in my youth. And I remember thinking, like, there are so many thoughts rushing through my head. I wonder if we traveled in a straight line for long enough, would we come back to the point we started the same way you would travel around Earth and come back to the same point you started? And how far can I see? How far are these farthest stars that I'm seeing? Are they super faint because they're intrinsically super faint? Or are these actually the brightest stars out there and they're just really far away? And so these were the questions I was asking myself. And yeah, we know the answer to them, but the answer isn't important. The thing that was important to me is that I loved this and I wondered about it. When I found Star Trek, or Star Trek The Next Generation more accurately, that added an extra layer for me to this. Because there are a lot of people I know who went the opposite direction of me, that they really got into science because they were into Star Trek. And I went the other way. I love the idea of being able to explore the universe, to excite our imaginations, to learn directly about what's out there. But with Star Trek, this added this extra layer of optimism, of altruism, of humanity using all that we learned about science, about technology, about ethics to build a better future for everyone, where everyone had a better life as a result of this. And that was just the optimistic, altruistic, science fiction setting I was craving as a young person. And so when the opportunity arose to say, oh, it's been 50 years since the original series premiered, and it's been 30 years, it was 30 years last year since The Next Generation premiered. Wouldn't it be great to write a book where we took a look back at all these different technologies that the different incarnations of Star Trek envisioned, and to say through a 2000 and lens, how far have we actually come? As it turned out, I went through 28 different technologies in the book. Only 4 of them require more physics than what we presently know to be plausible. Many of them are already here. Many more will be here probably in another decade or two. And there are even a few where what we've developed in the real world has surpassed what Star Trek envisioned.
That's crazy. It makes you really think about, if we've already come this far in such a short period of time, what does the future hold? In this sort of accelerating curve that we're on. But I want to talk just briefly about the next book that you're working on, because again, you are about to dance with a topic in cosmology that most cosmologists don't want to really engage with beyond, boy, it sure would be nice, but we don't know. So what's your strategy for taking on this next book?
The thing is, when you hear the Big Bang, most people think, oh, that's the beginning of the universe, right? If you ask yourself, how do we know that the Big Bang happened, right? This is a story that goes back to the 1920s, when we first discovered that the universe is expanding, right? So if you think, okay, well, the universe is expanding, I imagine it like a big ball of dough in zero gravity with raisins throughout it, and you're baking this raisin bread. And so what's happening is the dough is rising and all the raisins are expanding away from one another. Now, if we take that analogy, you say, okay, the galaxies are like raisins and space is like the dough. Really, the dough gets more diffuse, it gets filled with air, and that's what makes it rise. But in the universe, the dough is just the fabric of space itself. It doesn't stretch, it doesn't diffuse, you just make more of it as it grows. So these galaxies get farther and farther apart as you go ahead into the future. So you say, okay, well, what if we extrapolate back? And you say, okay, well, if it's getting bigger in the future, that meant it's getting smaller in the past. And you say, okay, well, what else happens when it gets smaller? Well, it gets denser because all those raisins or galaxies or whatever get closer together. So the density goes up. It also gets hotter. And this is because you say, okay, we have light, and light has a wavelength. So you say, okay, bam, wavelength of light. As the universe expands, space stretches and your wavelength gets longer. That means you get cooler. Longer wavelengths mean lower energies and lower temperatures. So in the past, shorter wavelengths mean higher temperatures and higher energies because your wavelength is shorter. So you go back in time and say, you know what? Now I'm too hot to form neutral atoms, because anytime I make a neutral atom, this high energy photon comes along and bam, it ionizes it. And you could go back even further and say, oh, you know what? I can't even form atomic nuclei because now the radiation is so short wavelength that it blows those nuclei apart. And you can go back and back and back to now it's energetic enough that I can just spontaneously make matter-antimatter pairs out of E equals mc squared. And now I can spontaneously restore these symmetries, these physical symmetries that are broken in our universe. And you say, okay, well, how far back can you go? You want to go arbitrarily far back. It's our instinct to say, let's go all the way back to a singularity where all the matter and all the energy and all the universe is compressed into an infinitely hot, infinitely dense point. And you can ask yourself from a theoretical perspective, if that were to have happened, what would our universe look like today? And the answer is it would be different from the universe we actually have. And that tells you something breaks down, something is wrong with extrapolating all the way back to a singularity. So that's, I think, the point that, this is the approach I'm taking, is to say, what's wrong with that picture? How is it wrong? And then how would you try to fix it? When any new theory comes along in science, from my point of view, you want to do three things to test your new theory compared with the old prevailing one. The first thing you want to do is you want to make sure your new theory can reproduce all the successes of your old theory, right? If you can't do that, right? If I said, oh, I came out with general relativity. If I can't reproduce all the successes of Newton's gravity, the theory that came before general relativity, I've got a pretty lousy theory. The second thing you need to do is the ways that this theory fails. How does my new theory fix it? How does my new theory make the correct postdictions that the previous theory didn't? And then the third thing you have to do is say, now I need to make new predictions, things we haven't yet seen or observed. And I need to make new predictions that are different from what the theory I'm trying to replace makes. Then we can go out and measure it, test them against each other and see, can I validate my new theory? That's the story that I take this approach to, is the theory of cosmological inflation, which is where we think the universe came from prior to the Big Bang.
Awesome. And what's the title?
The title's going to be Before the Big Bang. I have to fess up, it's a 10-chapter book. I'm only in the middle of chapter 7, so it's not done yet. But it should be done later this year, which should mean it's out next year.
Great. That's awesome. All right. So where can people find out more on all the places where you're producing content?
So I'm a little bit of a dynamo. I'm all over the place, which is to say you can find my blog, Starts With a Bang, on Forbes. We do 6 new articles a week, every week, unless I'm on vacation, which I might do like twice a year for a week. You can find me on Facebook. I run the page Starts With a Bang. You can find me on Twitter at Starts With a Bang. I'm on Google Plus as Ethan Siegel. I'm on Tumblr as Starts With a Bang. But my big other homes other than Forbes are, you can find me on Patreon. I write science stories and I do podcasts on SoundCloud. And I'm very excited to announce that in the next coming months, I'm working on setting up a studio and I will be making videos as well.
That's awesome.
So
yeah, I saw the pictures of your new studio coming together on Patreon. So good. I can't wait. And if you need any tips, tricks, and stuff, just let me know. I'll be happy to. And then of course we got to do some kind of collaboration to celebrate you being in the new studio. So that's fantastic. All right, so Ethan, you're going to stick around. We're going to cover some news, so we're going to hear more from you shortly. But before we move on to the next segment, I just wanted to give a big thank you to, of course, our good friends at the Weekly Space Hangout crew. This is the community of fans who really are the executive producers of the show. I think they booked Ethan. Wasn't up to me. Just happened. Here he is. Pleasant surprise. So if you want to take your sort of fandom and friendship with the show to the next level, Go to wshcrew.space and they'll put you into the Slack channel. That's the conversation that's happening down at the bottom of the screen. And they will put you to work helping to coordinate the show and figure out which guests you'd like to see in the future. So join that community. They're wonderful. wshcrew.space. All right, Morgan, let's move on with the first story, and let's go with the one about Europa, because that is absolutely amazing.
Which one? Sorry, you cut out on me there.
Europa.
Oh man, these are the coolest stories in my mind. Stories that sort of take a discovery that we've made recently and then sort of troll back through the heap of history to figure out, oh man, we could have figured this out, 20 or 30 years ago, if only we knew what we were looking for. So in this instance, a couple of years ago, observations made by NASA's Hubble and Herschel space telescopes caught evidence of what looked like water plumes coming off the surface of Europa. And this is something we've been looking for ever since Cassini discovered a whole bunch of water plumes coming off the surface of Enceladus, fed by a liquid water ocean. And we know Europa has a liquid water ocean and the same sorts of tidal stresses that Enceladus experiences from Saturn. And so the picture came together suggesting there ought to be water plumes, but we never really could see any. And Hubble made this sort of kind of tangential discovery, and Herschel suggested that it probably was true, but there wasn't really a solid foundation of evidence to say, yes, we absolutely found this. And that would be key for the upcoming Europa mission, which would want to carry instruments to study plumes if we thought they were there. And so this week, we found out from a group of scientists who had trolled back through data of a past mission to Jupiter, the Galileo mission of the late 90s and early 2000s. And they found sort of direct evidence of those water plumes from two separate instruments on Galileo. One is the magnetometer, which studies electric and magnetic fields, and the other is the plasma instrument that looks for patterns of charged particles moving around in Jupiter's intense radiation fields. And both of those instruments, during the same close approach, about 200 kilometers above the surface of Europa in 1997, gave signals that suggest the presence of a water plume. And so now we have, 4 instruments on 3 missions across 20 years, all pointing towards water plumes coming from Europa. That's about as determinable as you're going to get before you send a mission there directly looking for them. And that's just really exciting.
It's surprising that they hadn't noticed that data before looking through it, that's the kind of signal that you would be looking for as they approached and came within a close distance of Europa with Galileo.
Well, you have to remember that during the Galileo mission, they didn't know that there was water under the surface of Europa. That was a conclusion drawn sort of at the tail end of the mission by aggregating a lot of observations made over the course of the mission. And we had, and continued to have up until relatively recently, a whole different view of water in the solar system. 1997 was before we knew there was water in ice form in craters on the moon or on Mercury. It was before we knew of evidence of past water on Ceres. It was before evidence of water on Mars or geysers on Enceladus, or the fact that Pluto seems to be hydrologically active in interesting ways before all of this. And so had they set out to look for it, they probably would have found it. But it's one of those things that wasn't probably even really on their radar. They might have been looking for evidence that Europa had an ocean, but to think that somehow that ocean could connect to the surface and somehow produce plumes that would be detectable was probably, not even kind of on the whiteboard as a thing to think about when they were putting Galileo together in the 1990s.
Now, one of the things I heard about that I thought was very interesting is it seems like there's some evidence that unlike the plumes on Enceladus, Saturn's moon, it seems like the plumes on Europa may not connect all the way down to the deep ocean under the ice, that they might be from a much shallower portion on Europa. And so I thought that was a very interesting thing that came out of that study that showed, there may be more than one way to get a giant space geyser.
And those are the things that the Europa mission, which is often called the Europa Clipper by us planetary scientists, is going to answer. Because one of the instruments that Europa Clipper is going to carry is a ice penetrating radar, which from space will be able to blast radar waves down into the surface and look for where the water is, because water or radar bounces off of ice differently than it bounces off of water. And so they'll be able to sort of send down increasingly powerful blasts of radar until they find the ocean. And then as it makes these various passes, we'll be able to map the extent of that ocean and tell, okay, what's the depth of the main ocean? Are there pockets of water in other places? Are there fissures where there's a path all the way down to the surface? Those kinds of questions are completely unanswerable by our current data. We can make models that are constrained by the observations that we have, but there's a lot of unknown quantities about Europa that we'll be able to pin down very, very precisely when we're actually there with the instruments to sort of interrogate it intensely.
Absolutely phenomenal, and just I get so much more excited about seeing the Europa Clipper get back to Europa and to start answering these questions. So,
well, I'll throw in one other sort of related thing. This was going around Twitter a couple of weeks ago, that people stacked up a bunch of Voyager images of Enceladus and showed what looks like a pretty darn clear signal of the Enceladus plumes back during the 1981 flyby of Saturn by Voyagers 1 and 2. And so there's another story that if they thought in any way to look for that at the time, it could have been there. And they didn't really have the tools to do the image processing necessary in 1981 that is, trivial to do on a modern computer. But had they been able to do it, they would have found them. And had they found them around Enceladus, they surely would have been looking for them on Europa.
right.
And they would
With
have
Galileo.
and not only would they have maybe noticed it in the observations that they took, but they could have crafted observations specifically designed to look for those kinds of phenomena.
Right. Or
and it makes you
flyby.
wonder what
Yeah.
it makes you wonder what all is buried in the sort of trash heap of 50 years of space exploration that we just don't even today know to look for, that could totally change the way we do missions 20 years from now.
They had something similar with Tabby Star, right? That the data for its dimming was in the ancient plates
And the photographic plates from
right. So
100 years ago.
They found that it had a 20% dimming from like 1880 until the present day or so, including some variations.
yeah.
I also love that if you looked at the old Voyager data when they did their flybys of Saturn, you can see this tiny part of a structure on Saturn's pole that has those angular features,
Right, the hexagon
that we now know are that hexagon.
Yeah.
That's around the poles. But when the Voyager data came in, there were a combination of factors. One was that it was winter in Saturn's northern hemisphere, so the pole was tilted away from the sun, so you couldn't really see that much of it. But another was we didn't know to look for it, that we could have discovered, there is a polar hexagon on Saturn as well, 30 years before we actually found it.
Same thing happened with New Horizons. If you overlay like a 1990s or 2000s Hubble image of Pluto over the canonical Pluto image of New Horizons, you realize the heart was there all along. And it was just like 5 pixels.
Yeah.
But it was there. It was lighter. It was exactly where we saw the heart in Tombau Regio. It was there for 100 years, and we couldn't notice.
Yeah.
But as soon as we knew what to look for, it just hit you right in the face. It was always there.
All right, well, let's move on. There's too many more excellent stories this week. And I would add, I was going to add more stuff, but I can't do it. Let's just move on. So my story this week, my first one, is we're going to be talking about the new helicopter that's going to Mars, and I'm going to play a video here for the folks who are able to watch. Apologies to the people who are listening on the podcast, but so NASA announced that they're going to be attaching a tiny little helicopter. It's only 4 kilograms, I believe.
4
kilograms?
pounds. It's like
4
less
pounds,
than 2 kilograms.
Yeah, 1.8 kilograms with the Mars 2020 rover. And it's going to be solar powered. Its rotor turns at 3,000 RPM. It's going to be able to do these sort of short hops on the surface of Mars. And it's going to be tagging along with the 2020 rover. And so the plan is that it's going to join the rover. The rover is going to land on the surface of Mars. It's going to drop the helicopter down, and then the helicopter is going to, or the rover is going to drive away from the helicopter, and then the helicopter is going to make some flights. And they're hoping for, I believe, 5 flights is sort of the kind of technology they're going to be able to do. So I'm showing a sort of a video to the people who are watching this, and this is inside essentially a simulated Mars environment. So it has the same pressure and temperature of Mars, and this thing is flying just great in this reduced atmospheric pressure, which is just absolutely amazing, totally mind-bending. I'm really excited about this.
Yeah, I did a video for SciShow like maybe a little less than a year ago about this helicopter, and I had a chance to sort of really dig into what went into it or what's going to go into it. And for my money, this is like one of the coolest engineering things that NASA has ever done, because it's not that this helicopter can carry 1.8 kilograms. It's that the rotors plus the solar panels plus the battery pack plus the motor plus the computer plus the camera plus the radio system all add up to 1.8 kilograms. And yet it can operate autonomously from the rover, and do so while taking into account the winds on Mars or the changing terrain of Mars. You know, it can only fly for 90 seconds at a time, and it has to be able to do all of this stuff on board a computer that's a tiny piece of this package in that amount of time. And just to pull that off at all is amazing. And then to pull it off on another planet, and the opportunities that it'll open up for helping Mars 2020 explore could just be tremendous for improving the efficiency of the rover.
And this is one of those examples where NASA is testing out sort of a new set of technologies. They're expecting 5 flights. Like any drone pilot, it's just a matter of time before you crash it and it's destroyed. And I'm sure Mars 2020 is going to smash up its pretty drone, as soon as it opens up a Christmas present. But to think about this sort of future idea where every Mars rover is sent with a fleet of autonomous drones to be able to explore the landscape around them, just absolutely multiplies the kind of science that can get done by the rovers and all of this additional science. And right now, the tiny little drone is designed to be completely autonomous. Like, it's gonna, once it detaches, it's gonna have everything that it needs. It's gonna have its batteries, it's gonna have its solar panels. But you can also see this idea. I mean, it can be communicating its data back to the rover, and then the rover is going to be communicating its data up to orbit, and then the orbital spacecraft are going to be communicating that data back to Earth. You can see this infrastructure building for the scientific exploration of Mars, and that is fascinating. What if you send a care package with 10 more drones that land near the rover, and they all can then get to work and do even more science and multiply the capacity of the rover itself. So when we think about the rover that's potentially going to be going to Titan, think about some of the kinds of things that could be going to Venus. It's a really exciting development, and I'm really glad that NASA is pulling it together to send something that's going to fly in the atmosphere of another world. Amazing.
If you're into reading the tea leaves of NASA, and who isn't, I think this is probably a positive sign if you're looking for the Titan helicopter in the coming Discovery proposal. It's clear that they're comfortable at some level with the idea of these autonomous helicopters. And there's a whole bunch of things that are easier about flying in Titan, a whole bunch of things that are harder about flying on Titan. But if they had canned this copter that they've been working on for years, I think that probably would have been a bad sign. So for the Titan mission. So the fact that they are choosing it maybe isn't necessarily a good thing, but it's not a bad thing. And I think that's awesome because the Titan copter is obviously the cooler of the two Discovery missions.
Yeah, totally. All right, Ethan, we're gonna have you return. And speaking of topics that most people don't want to touch with a 10-foot pole, let's talk about this research that came out of, was it Durham, about multiverses and the possibilities of life in these other multiverses.
The researchers that came out with this study, what they were looking at is they said, we know how the universe evolves today, right? We have this state, we have the ingredients, and we know the initial conditions, and therefore we know how the universe came about to form through simulations, stars and galaxies and the ingredients for life that could possibly have given rise to human beings, right? There are a lot of things you need to happen. You need to have dense enough clumps in the young universe that over time they can gravitate together. If something is balanced wrong in your universe, like you have too much dark energy, or dark energy of the wrong sign, or you didn't have enough matter, or you had too much matter, your universe could do catastrophic things, like it could recollapse before it had time to form stars or galaxies. Or everything could expand away too rapidly, and then you wouldn't even be able to form stars or galaxies. Now, dark energy didn't have to exist in the universe, we don't think, but it has a certain value. And interestingly, people had said, wow, this is weird. Somehow dark energy has like the maximum value it's allowed to have. And if it was stronger, either positive or negative, you would have either recollapsed or been unable to form the structures that lead to human beings. And this new study, the big part that's groundbreaking about it is it actually runs those simulations with all these different values of dark energy and finds, you know what? Dark energy could have been 3 or 10 or even 50 times as strong as it is in our universe. And that would really only change star formation by about 15%. That you would still form stars and have these bound structures and form many generations and have these organic molecules naturally arise in interstellar space. You would form rocky worlds around sun-like stars, and bam, that's as far as we know all the raw ingredients we need for life. Now, things might need to get lucky in a number of ways to go from non-life to life, from life to complex differentiated life, and from that to intelligent, technologically advanced life. We don't know all of those intricacies, but we do know now, thanks to this study, that if we have this enormous multiverse, and this is a big if, we're not sure, if all of these different multiverses have different values of the cosmological constant of dark energy, then things are not as finely tuned as we had assumed. You don't need the specific value of dark energy we have in order to have a universe that looks kind of like ours, that has potential observers like you, me, and all of the listeners. What we have instead is a universe where, you know what, as long as dark energy is below this certain critical value, and this value is, by the way, like 50 times or more larger than what we have in the universe today, then you can have potentially planets, human beings, intelligent aliens, whatever you want.
Right.
That's the important result that came out of the study. But what it can't quite tell you is what's more likely or less likely in the multiverse.
Right. I mean, that's sort of an argument that people sometimes have, is like, oh, it really seems like the universe is perfectly tuned for life. But it kind of feels like the universe, if it was any worse, then life couldn't form. Like, it's about as, it's right on the edge. And I guess people were thinking, oh, there could have been, the chances are greater with dark energy, with, as you say, the cosmological constant, with the force of gravity, with the strong nuclear force, all of these different constants that exist in the universe, but actually that they're all so tightly focused, but actually there's a little more flex to some of them, so you could have more combinations where maybe you could have life, but they have a little more dark energy they have to contend with, or a little less gravity, or what have you.
So here's what the authors sort of argue, because what we know that there is actually a lot of wiggle room in a lot of these cases, but what the argument goes for this particular problem about dark energy cosmological constant is, if you were to be super naive and say, I don't know anything about anything, but I want to try and estimate the cosmological constant, what you would do is you would write down your equations and you would look at that cosmological constant term and you would say, what kind of units do I need in this cosmological constant? It turns out to be proportional to a mass to the fourth power. And you say, okay, which mass should I use? Well, I can make a mass out of fundamental constants. Let's try that. So you take G, the gravitational constant, you take C, the speed of light, you take H bar, Planck's constant, you combine them together, and you get a mass out. That mass is known as the Planck mass, and it's about 10 to the 19 GeVs, which is about 10 to the 19 times the mass of a proton, give or take. Then you say, okay, well, if I put that in there, what do I get for the cosmological constant? And you get a value. And then you say, well, now I'm going to go measure dark energy and infer what's the cosmological constant. And you get a number that's 120 orders of magnitude smaller. It's off by a factor of 10 to the 120. So if you didn't know anything, you'd say, I predicted this enormous value and I observed this tiny value. Things seem really finely tuned. So this is where you hear people say things like, oh, but landscape, right, and multiverse, and if you have 10 to the 500 possibilities, then surely some of them will have the small enough value that you can wind up living there. Not a very convincing argument to me, but it convinces some. Instead, what this study showed is, if that were the case, then what you would wind up with is most of your universes that actually had aliens in them, that actually formed structure, like would give rise to things like us and planets and organics and all of the interesting things, they would be right at that upper limit threshold. You would be 100 times more likely to have something that was, only finely tuned by 118 orders of magnitude than you would by 120 orders of magnitude. So why then do we find ourselves living in a universe where the cosmological constant or dark energy is so much smaller than that maximum value? Right. Now, again, this takes an assumption, and it takes an assumption that I personally, and when I say personally, I mean professionally, don't like. When we see something that looks finely tuned in nature, we can say, yeah, well, all the possibilities existed and we picked one out and this one happens to be us. That's pretty lazy. Usually in physics, what we try and do is we say, hey, here's what we naively predict, here's what actually happens. What are the dynamics? What is the cause behind why things turned out this way? And for dark energy, we don't understand it well enough to know. We don't understand why the fabric of space itself seems to have this particular amount of energy inherent to it. In fact, we don't understand why it appears to have energy inherent to it at all. So yes, it's neat that this new result shows you, hey, if you made this assumption and you said this is how things are finely tuned, we're actually in a relatively unlikely state. But it's more interesting to me to say, hey, things could have been different by this bendy amount. They could have been 3, 10, 50 times greater or infinitely less great, and we'd still get a universe like us. That's the interesting part to me. But the bigger question that we still don't know the answer to is, why does the fabric of space have the energy inherent to it that it actually has?
Right. Yeah. Not covered by this study, or, and if you can figure it out, then you get your Nobel Prize.
Someone else will steal it. Don't worry.
Morgan, let's talk briefly about the International Space Station.
It's still up there.
Whew.
But not necessarily for that much longer. The US is currently planning to pull out and deorbit the ISS in 2025. That was a decision made during the Obama administration and reaffirmed by the Trump administration. But there were hearings on Capitol Hill this week about whether that was the right thing to do. And sort of interestingly, from one perspective, we saw two senators, Republican Ted Cruz of Texas and Democrat Bill Nelson of Florida, agreeing with each other, which itself was a pretty unusual thing, but agreeing that to their mind, it didn't make sense to give up on the U.S. investment in the ISS. Even though it's costing NASA somewhere in the neighborhood of $3 or $4 billion a year to operate it, that's a pretty small price to pay relative to the money it costs to build it. And depending on how you account that, it's probably somewhere between $100 and $150 billion. And given that enormous upfront investment, shouldn't we keep using it as long as possible? And I'm actually interested to hear what Ethan thinks. We've hashed this subject 1,000 times, and generally I would say scientists are not in favor of the ISS as a source of useful research. But it does offer some opportunities that aren't available elsewhere. And we have this sort of sunk cost problem where we've already spent a bunch of money on it.
I mean, my thoughts are, I'm a big fan of infrastructure in space. And what the big scientific advantage to me of the International Space Station is not like, hey, we can send people up there and see the effects on human bodies, or we can send people up there and we can have a zero gravity environment for us to do little experiments in. For me, the International Space Station represents the best Earth observing location for a series of missions that we presently have. Rather than having a series of standalone missions, the ISS is uniquely positioned to observe the Earth continuously. And so for me, I think, NASA, as it is structured today, from a science point of view, it has 4 major objectives. Astrophysics, which is my deal, planetary science, Morgan, which is your deal, heliophysics, which is someone's deal, but no one's here, and earth science, which is all about using what's up in space, using our perspective above the surface of the Earth to study what goes on our planet. Now, I have seen huge proposals to gut a large number of Earth science missions. You have seen them too. I have seen NASA and NOAA ceasing to do studies it has been doing for decades to create these huge long baseline records of carbon dioxide, of temperature, of all these properties of a planet that we know we as human beings are modifying on a planetary scale. I think choosing to deorbit the ISS with no alternative to replace it or to run these missions otherwise is largely a political move geared at defunding NASA Earth science. So for me, yeah, it is expensive to keep the ISS up there. Is it the best investment of resources? Probably not, but it is the one we've chosen. But the thing is, for me, we have all of these missions that are currently operating on the ISS. The ISS has the infrastructure to continue operating these missions and to operate new missions on it in the future, a large number of which are already part of NASA's mission timeline. And so choosing to deorbit the ISS is an announcement to the world saying, we don't believe NASA should be doing Earth science, and we don't think this is an important thing to value. As someone who lives on this planet and has no plans to stop doing that,
Yeah.
I am in favor of keeping the ISS.
Yeah, it's interesting to sort of see as people kind of run through these questions, like, do you want to deorbit the ISS? People are like, well, no. And like, do you want to launch the SLS? Well, yes, but also I want SpaceX to get, to bring the costs down. I mean, I think that I think where you were kind of going is like the International Space Station is the most complicated machine that humanity has ever built, the biggest machine, again, that's ever been created. It shows us how expensive flying to space currently is, and the prices to refuel it and the prices to resupply it. This is just the reality. Could you make it cheaper? I'm sure you could. I'm sure you could knock the prices off by half, really get SpaceX to sharpen its pencil for resupply missions with the Dragon. But we live in this fantasy world about the kind of space travel and space exploration that we would like to happen in the future when the BFR is flying. But right now we need to get to that reality, and the way we do that is to learn all these little lessons about maintaining orbit, about scrubbing out carbon dioxide, about how to keep humans from dying while they're out in space. And at the same time, as you say, it's this platform for being able to observe the Earth and really recognize our context with it. So and to what Morgan said, like, let's just keep the thing going for as long as we can as the ongoing investment. I would like to see, personally, it used more as a platform to go further, to go, okay, let's try sending up a crew, and their job is to detach from the International Space Station and go to a different orbit and survive for a week and then come back to the space station. What logistics were involved with that? Start to learn some of those lessons about more deep space exploration using the International Space Station as a starting point. But again, that's just me. One quick piece of news that I wanted to mention as well was this week on Friday? Was it Saturday? Man, it's all starting to blur to me now. No, it was Friday. The new Falcon 9 Block 5 rocket launched, carrying a satellite for Bangladesh. And the Block 5 is theoretically going to be the final stage of construction of the Falcon 9. And this is its most reusable version. And the cool thing about the Block 5 is, launched successfully, landed on its drone, was pulled back into dock, and from this point forward, in theory, there should be no servicing required on the Block 5. They're going to take the thing, put it back on the launch pad, they're going to refuel it 10 times before they do any servicing of the rocket at all. And in theory, it should fly 100 to 300 times before it has sort of reached the end of its life and needs to be retired. So in theory, SpaceX is going to build a couple of dozen of these Falcon 9 rockets and not need to build them anymore, part to replace whatever ends up breaking down, as opposed to this constant construction of new rockets. So from that perspective, we really are truly reaching this point of reusability and trying to make rocketry more like the commercial airline for the first stage anyway. And then we'll see what happens with the upper stage and the fairing and things like that. So very exciting news. All right, well, I think we've reached the end of our show, a couple of minutes over. So why don't we wrap things up? Morgan, tell me something interesting that you're working on.
Well, I had another awesome video come out for SciShow Space this week about 3 current mysteries facing us with respect to the Milky Way. So that's pretty awesome. You can check that out over on their YouTube channel. And I've also been thinking a lot this week about, I've been obsessed with these really, really old recordings made all the way back to the 1860s that they didn't even know how to play back. But we've started to be able to scan them in digitally and basically use computer algorithms to play them back. And they're like these little time capsules from so far in the past. And I just think that's such a cool application of technology.
They're able to like read with like a laser, right? To be able to read these things, right?
Right. Yeah. They sort of figured this out in the 1860s, how to make recordings on these drums. But apparently it didn't occur to anybody that you could play them back until like 20 years later when Edison built the first phonograph. And we have some of the very original phonograph records from that period, but we also have records from these earlier periods where they were sort of doing this basic physics research on how sound waves work. And now we can listen to the sort of things that they were saying into their receivers as they were just watching these patterns be made. And I think that's just really cool.
All right, Ethan, you get the last word. Tell me a project that you just worked on apart from your book, which we've mentioned, and I will hold up one more time: Treknology, the Science of Star Trek, from Tricorders to Warp Drive. What's something that you just posted to Starts with a Bang?
You know, I think for your listeners, there was a story that just came out today in the journal Nature that I'll have a story on tomorrow for Starts with a Bang, about the very first stars that formed in the universe. What we just observed, what they just confirmed is, you know, we're always looking around galaxy clusters to see where this light bends around them. It gets gravitationally lensed, it gets magnified, it gets stretched, and it means we can see farther than we can any other way by using this natural amount of gravity from these galaxy clusters to enhance the light coming from behind them. So we find all these candidate galaxies. We just confirmed the second farthest galaxy of all time. Its light comes to us from just 530 million years after the Big Bang, when the universe was less than 4% its current age. What's remarkable about this galaxy is, for the first time, for a galaxy this far, we've detected oxygen in this galaxy. And from the brightness of the galaxy and the amount of oxygen we detect, we've been able to determine that the stars in that galaxy are over 250 million years old. We believe we have found direct evidence from stars and molecules that we had first formed stars in the universe when it was only 200 to 250 million years old. Now, what's very interesting is this lines up with a study of neutral hydrogen and the hydrogen spin flip transition, right? When you have a proton and an electron, they can either have opposite spins or the same spins. And when they have the same spins, they flip on a time scale of about 10 million years, and they emit a very specific photon. We looked at that photon signature and found, it looks like there's this big dip in that signature showing us, hey, we think we made ionized hydrogen, which means we had a burst of star formation, peaked when the universe was about 200 million years old. We have not yet seen the first stars. Hubble can't see back beyond about 400 to 500 million years. We're going to need the James Webb Space Telescope. But in the interim, these are the very clever techniques we're using to learn about these dark ages and cosmic dawn, when we went from a universe with no stars in it at all to a universe full of light.
All right, and that's tomorrow. Spoiler alert. That'll be tomorrow on Starts with a Bang. Awesome. All right. Well, thanks everyone for watching us today. Really appreciate it. Thanks to our special guest, Ethan Siegel, and of course, Morgan Renberg, for joining us here on the Weekly Space Hangout. Thanks to the Weekly Space Hangout crew. Go to wshcrew.space to sign up. Thanks everyone in the YouTube chat, and we will see you all next week.